Okay, welcome back everyone. In this video, we are going to be looking at the magnetic field that is actually produced by a wire itself. So in order to do this, first we want to start with what's called the Biotsavart Law. And this says that the magnetic field dB produced by a small amount of a current element di is given by the following equation. So don't worry about all the constants, but the thing to focus on is that we still have the cross product in here, and it's basically the same thing as before, but this is kind of an empirical law. Now if you integrate this on a closed loop, so if you integrate dB going from 0 to something like 2 pi r or something like that, you can get the magnetic field of a wire. And we'll look at this in much more detail. So here's a wire, and here's the magnetic field, which is circulating around that wire. And it has the value of mu naught I over 2 pi r. Now the direction of this is determined by the right-hand rule. And this is right-hand rule number 2, which says that I is given by your thumb, and B is the curl of your fingers. And we're going to prove where this comes from a little bit later on. So again, we want to place our right hand so that our thumb goes in the direction of the current, and then our fingers will curl in the direction of the magnetic field. So it's going to curl around the wire. And if we're to look at this head on, we would see the current coming out of the page and the magnetic field circulating around like this. You can try that. Point your thumb at your face and you can see your fingers curling around that. If it helps, hold a pencil and curl your fingers going around that pencil. Likewise, if the current is going into the page, point your thumb down into the page, then you're going to get the magnetic field going opposite of that. So try it. On the left, try putting your thumb pointing into the page and see how your fingers curl around in a clockwise direction. On the right, do the same thing with your thumb pointing out of the page and see how your fingers curl in that direction. And also notice how these field lines are farther apart as the distance from the wire increases. That's because of our B equal to some constant over R. Okay? So it's a 1 over R thing. And we can see that as well here. Okay, so now we're going to take a moment and we're going to talk about parallel wires and the forces that they cause on each other. So we have to be very careful when we draw this. We're going to have two wires and we're going to call them I1, and the other wire is going to be I2. But I'll do I2 in purple. And we want to define the magnitude and direction of the force they exert on each other. Now let's go back to what we just did and let's draw the magnetic field of each wire. So if you think about wire I1, your thumb would be pointing up and your fingers would be curling around that. So that means that on the left side of I1, the field would look like it's coming out. And this would be what we call B1. And on the right side, it would be going into the page. That's also B1. And remember that the value of this field is mu naught I1 over 2 pi d, where d is the distance between these two wires. Or actually, it would be r in general, but it's d between the two wires. Now, the interesting thing is that even at the location of I2, there is a field from B1. And so what we can do is we can determine the force that wire I2 experiences because of field B1. So this is going to be F is equal to I2 L cross B. And this is going to be the force of 1 on 2. And this would be field B1. Likewise, we can calculate the force of wire 2 on 1 as equal to the current of wire 1 times its length cross the field that 2 creates. Now this is the important point here, that I2 experiences a force because of the field that I1 is making. I2 does not experience a force from B2, and I1 does not experience a force from B1. Just like you can't pick yourself up. A wire can't exert a force on itself. There has to be an interaction between two things. So, thinking about our right-hand rule, we're going to do the force of 1 on 2 first. And I2, your pointer finger points up. B1, which is in red, is actually pointing into the page. So your palm should be pointing into the page. And the force, therefore, is pointing to the left, the force of 1 on 2. Now, we can do the same thing for I2, and let's draw the magnetic field that I2 is creating. Now you have to be careful about this, but to the right of I2, it is also going into the page. So these fields kind of add up in that sense. And to the left of I2, its field is coming out of the page. So that means that even over here at the location of I1, it's coming out of the page. So this is B2, and this is B2, and this is B2. It's kind of a busy diagram, so you have to really think about what's happening here. And notice that in between the two wires, the fields are in opposite directions, so they could cancel out potentially. And some of your homework problems ask about that. Okay, so what's the force from 2 acting on 1? Okay, your pointer finger points up. Your palm, representing the field, must point out of the page. So I have to flip my hand so that my fingers are pointing up and my palm is pointing out of the page, and my thumb was pointing to the left. The force of 2 on 1 is to the left. So what's happening to these wires? They are being attracted. So this is just a rule of thumb that we'll review in a second. But let's calculate the magnitude of the force. So the magnitude of the force of 1 on 2 is actually the same as the magnitude of the force of 2 on 1, and we'll see that in a second. So F1 on 2 is I2 L B1, and everything is perpendicular. And that's equal to I1 L B2. Let's just focus on the left side. I2 is a given, and we'll assume that we know L, but how do I find B1? I have to look up here, and it turns out that B1 is mu naught I1 over 2 pi d. So d is the distance between the wires because that's the location at which we're trying to find the magnetic field. Now you'll notice that if I plug it in on the other side, B2 would be mu naught I2 over 2 pi d. So what this is telling us is that the force is equal to mu naught L I1 I2 over 2 pi d. That's the magnitude of the force between the two wires. Now sometimes what you'll see is the force per unit length, which is just this. so nothing too exciting. Force per unit length. Okay, but notice what happens is that these forces are going to be equal and opposite. And even though you have I2 outside of the field calculation for one of them, it's inside the field for the other. So things get switched. All right, now what if we have parallel wires that have currents in the opposite direction? So that means that perhaps I1 is going up, and let's do a different color for I2. I2 is going down. Let's find the magnitude and direction of the force they exert on each other. Well, the magnitude is going to be the same, and it's going to be essentially mu naught L I1 I2 over 2 pi d. That's what we saw in the previous slide. So let's look, since we're on red, what's I2 doing at the position of I1? Well, now you have to point your thumb downwards because that's the direction of the current. And you curl your fingers, and your fingers are actually going into the page anytime you're to the left of I2. So this is really B2 that we're drawing here. But then when you're to the right of I2, your fingers should be coming out of the page, and so we draw B2 going that way. So that means that at the location of I1, the field is going into the page, and if you point your finger up and you put your palm facing down or into the page, then we have a force, I'll do a different color, that is to the left. But what about for I1? Well, I1 is going to produce a field that to its left is going to be coming out of the page. Remember, your thumb points up and you have to wrap your fingers around. So that's B1. And to its right, it'll produce a field that's going into the page. So that means that at the location of I2, it's still going to be going into the page. So that's B1 and B1. So your thumb has to point, your fingers have to point down because that's the current. Your palm points into the page, and your thumb will therefore be pointing to the right. And this means that opposite direction wires will actually repel each other. The forces will be pushing away. So there's the summary. Parallel currents will attract each other, and anti-parallel currents will repel. So that wraps up the material for this time. Next time we're going to be looking at a very important concept, Ampere's law, which tells us how to calculate fairly easily the magnetic field around a current.